Hi, everyone. My name is Emily Wenger, and I'm here to share with you about our work building data isotopes for data provenance in deep neural networks. This work is joint with Jiu Li, Benjao, and Vitaly Shmidakov. In case you haven't been paying attention the last few years, machine learning is now everywhere. It's in browsers, it's in our mobile phones, it's used in finance and healthcare and cars, and in everyday web and computer applications. Despite the ubiquity of this technology, there are not a lot of regulations and controls that have been codified by law. As of 2024, we have the EU AI Act and GDPR, and around the United States, there are scattered biometric laws focusing more on facial recognition and other biometric applications of machine learning. Notably lacking are laws guaranteeing transparency in data use in these machine learning models. There are no legal frameworks mandating any form of transparency or ensuring that meaningful consent is obtained in collecting training data. Since often data used to train machine learning models is collected from large-scale scrapes of the internet, individuals' data can be harvested and used without consent or their knowledge in machine learning models. This then begs the question, without any legal framework to support them, how can individuals know if their data is being used in machine learning models? And that motivating question is what drives our proposal today, a tool called data isotopes that enables individuals to have a bit more agency over understanding how and if their data has been used. So let's dive into a motivating scenario behind data isotopes to understand how and why it works. So we have this person, Alice, and Alice has shared some images online to different social media sites. And after a couple of years or even weeks or months pass, Alice notices that one of the platforms that she shared data to has offered a new image classification model. And Alice is curious, did they use my data to train this model? Given the lack of legal frameworks, Alice can't, query the provider and ask them specifically, did they use my data? So the alternative route Alice can take is using our mechanism, data isotopes. Isotopes are images that are modified in certain ways when shared to make their presence in machine learning models downstream more detectable. To understand the setup and possibilities for data isotopes, let's first make sure we understand what Alice can control in this scenario. So at the top here, we have the flow of information in a data collection pipeline. We have Alice, who posts information to a platform. And at some point in time, a collector comes along and collects the data, images in our scenario from that platform and gives them to the model trainer. And the platform and the collector and the trainer may or may not be different entities. The collector and the trainer have the most power. The trainer can change how the model training proceeds, and both the collector and the trainer can assign data labels and change them to be perhaps something unexpected. However, it's unlikely that they will do much to modify the content of the data that they have because it's valuable to them and they collected it. So it seems reasonable that they would keep that unchanged. We assume the platform is kind of neutral here and just hosts information, which really means that Alice can only have some confidence that she controls the content of her data because that is what is valuable to the machine learning trainer. So that means that the real goal here is for Alice to build, or for us to build a mechanism that Alice can use to detect unwanted data use only by manipulating the content of her data. And that's a pretty lofty goal. To just further clarify the threat model, let's just look at a few other assumptions. Alice really has no knowledge of other users' data that's being collected alongside her own. So we can't rely on this in building our mechanism. And that stands in contrast to prior work, which assumes that there is broad knowledge of all the data. But that is just not true for Alice. Additionally, Alice can't really change the labels of her data as we saw. So that means that provenance mechanisms via things like backdooring are not super realistic because changing the label would immediately destroy this mechanism. We also assume that Alice doesn't know really what the downstream model looks like. We can assume that she knows that it's perhaps a classifier and has some sense of what class her images might be grouped into, but she doesn't have broad feature space knowledge of the model, and so can't use things like clean label poisoning. And finally, we assume that she really only has query-only access to the model, because that's typically what's provided. So she can't inspect it to see if her data has left a specific type of mark on the parameters. All of this together means that existing solutions are insufficient and assume too much power on Alice's behalf, which motivates us to design our simpler solution with much fewer assumptions. So specifically, data isotopes work as follows. Alice marks the images that she posts online that should be grouped into a class with a spurious feature, a feature that is not characteristic of her class in the model. And this creates a data isotope. So in just a face recognition scenario, for example, Alice would add this little mark like a turtle blended into the background of her images, some of them, to create these marked isotope images. Then if these images are used during model training, the spurious feature, the turtle, is learned as being associated with Alice's class in the model. And Alice can then employ this spurious feature in a testing procedure to detect the use of her personal data. The key intuition here is that the presence of the isotope feature in Alice's class changes the model's probability predictions. It doesn't change necessarily the hard label prediction, but it can change how the distribution of labels looks. Specifically, training on isotope images will increase the probability of Alice's label for images with Alice's mark, regardless of their true class. As an illustration, here's a model trained on isotope images for class 7, where Alice's class is 7. If we then query this model with a different image of a different class, like label 0, we can see that in the base case, label 0 is the highest probability, and Alice's class in light blue here has a probability of 0.01. These are not drawn to scale. If we then add Alice's isotope mark to this image, you can see in the probability distribution that Alice's class probability jumps tenfold from 0.01 to 0.1. And if we observe this effect consistently over multiple images from multiple labels, we can have some reassurance that this model was indeed trained on isotope images, and therefore Alice's data was used. We evaluate isotope performance under a variety of experimental settings, looking at object and face recognition scenarios with up to 500 classes in the base scenario and 1,000 classes in an additional test we do later. Really, what we want to know is how well isotopes perform under two key parameters. Alpha, which is how visible the isotope is in Alice's data, and rho, which is the proportion of the class label that is marked. Ideally, we want isotopes to be consistently detectable even when alpha and rho are very low, meaning that few of Alice's images are marked quite faintly. The metric we use to evaluate isotope performance is this thing we call V of T, which is the true positive rate of an isotope verification procedure described in the paper. Essentially, what V of T says is what proportion of the time does the verifier correctly detect that isotopes were used to train this model? Here is just a base evaluation setting for isotopes. This is performed on the PubFig data set with several different classes marked, which is why we call it a multi-isotope performance. The heat map here shows isotope verifier true positive rate as rho on the x-axis, the proportion of data marked, and alpha on the y-axis, the mark visibility vary. What we see here is once alpha is above 0.3 and rho is above or is roughly 0.1, we can really consistently detect the isotope. This means that even if only 10% of Alice's data is marked somewhat faintly, we can be sure that isotopes are detectable. We also measure something called mark distinguishability, meaning how can we tell if different isotopes belong to different classes, and that is also high under these settings. We investigate a few additional questions in our paper surrounding isotope scaling. We find that isotopes are successful in models up to the 1,000 class ImageNet dataset, where 100 classes contain isotopes. We also test whether isotopes perform well in an ML as a service setting where we have no understanding of what's going on under the hood in model training. And there we have basically a 90% success rate. And then finally, we investigate transfer learning and whether isotopes perform well in that setting, and we find that indeed they do. We also evaluate numerous countermeasures that a model trainer could use to defeat or otherwise deflect isotopes. And we find that all of them either fail or impose significant costs on the model trainer. And that's discussed more in our paper. So finally, we have proposed a data isotopes mechanism to enable practical data use auditing, and we find it is robust against reasonable countermeasures. Future work can and should explore the applicability of isotopes in other domains like voice and text and generative AI models, and could explore theoretical explanations for their success. We believe isotopes are a tool that can help supplement the existing dearth of legislative options for ensuring data transparency, and we look forward to seeing future extensions of this work.